Welcome to a new lecture. In this lecture, we're gonna talk about introduction to microprocessor system. So, what is a microprocessor system? A processor that's in the size of micro. Nice. Okay. So, a microprocessor system is a IC that processes instruction. Okay, a IC that processes instruction. So we know that we have CPU. Assume this is a illustration of CPU. So in the CPU there are certain stuff. So in there we have a chip that's called as microprocessor. So this microprocessor processes instruction. Okay, so we have our own programming language such as Python, C, Kotlin, and so on. So these programming languages are a language that is in English that could be easily translated and easily understood by humans. So this programming language actually has compiler, which actually compiles the programming language, translates into assembly language, which is then translated to hex code, which is then translated to electrical signal by this microprocessor. Okay, so this microprocessor takes assembly to hex, then the hex to electrical. So here in the electrical part it's already going to analog electronics, whereas here it's digital electronics, and above it is all the one that we are studying in algorithm, programming, and so on. Okay, now a microprocessor system is a system where the IC is processing the instruction. It's the microprocessor. Now, what it actually does is it fetch, decodes, it executes instruction, which means that if I say x is equivalent to x plus 2, so this could be translated to move 0010, sorry, it could be move B0010, and then it could say add A B, move CA. So technically it takes 2, it pluses with A, which is our initial X, then it moves to C where our new X is stored. So this is what programming by human, and this is what programming does in the assembly language. Sometimes we need to do our own programming language in the assembly method. Now it actually fetches the code, it decodes the code, it executes the instruction, then it has ALU, arithmetic logic unit, controls data and flow between memory and IO, which means that they have this internal process running in them. Okay, so I said that this small illustration of CPU contains ALU, contains control unit, contains output devices, input. Okay, this is not contained, but it has a bus and it has memory. Okay, now what is actually bus? A bus is a pathway which takes the data. So it's not one data, two data. Assume or imagine that you are in a bus can contain around 40 people. So make it in a multiple of 8, it could contain 32 people. So same, bus is something that carries data to the devices. It could be memory, it could be output, it could be input to control. It takes a bus full of data, it transfers. Control to output, it takes the bus full of data, it transfers. So the path is considered as bus. Okay, now in CPU there are registers. Registers are the smallest available memory that we can have. So registers can store memory up to 8 bit. 8 bit means 1 byte. Okay, so registers, which is B, C, D, E, H, L, we have 6 registers. I'll show you in a sec. And then we have ALU, which is addition, subtraction, and OR gate, NOR gate. It's not gate, but it's the operation that's in it. Control unit means which allows you to control in order to move data, fetch data, and all. And we have the microprocessor itself. Microprocessor, it's a combination of these two, both control unit and arithmetic logic unit. Then we have bootloader. Bootloader is a system program that actually boots the operating system. You could have maybe in my machine I could have Windows, in your machine you could have Apple, but both machine could use the same processor. So the bootloader is just a processing mechanism that actually loads the operating system, then buses, as I said, the path, and interrupts is a physical button that actually interrupts, or a interrupt mechanism is where if I input my mouse, suddenly the machine goes silent and the machine actually makes the mouse to transfer data, so that's interrupt. So this is a memory system. Memory system will be additionally and fully explained in the upcoming lectures, but we'll see a small explanation on what is memory system here. So this is how the memory looks. The memory will be in multiple of 8, so it means that 2 to 8, or it could be 2 to 32, or it could be 16. So these are the n value. And in our memory we have stack area, data area, program area. So stack area is where we save the instructions, data area is where we save our data, program area is where we save the programmable stuff, the virtual stuff. So logical means programmable, we separate that stuff specifically for programs to use, and physical means the actual memory where the data is used. So more will be explained in the upcoming lectures, do not be worried. And then we have the memory hierarchy. So registers, as said, small and closer to the CPU. Then we have the cache memory, which is smallest too but near the CPU. Then we have main memory RAM, which is volatile. Volatile means, okay, these are all volatile. It means that if you power off the system, when the system goes off, technically cache memory does have the system, but does have the memory cached in it, but registers and while RAM means when you power off the system goes off, you don't have any data in it. Okay, then we have secondary memory, and this is random, means you can access wherever you want, you can access wherever you need. Then we have secondary memory, which is HDD SSD. This is non-volatile, meaning that if you don't give power, so the last time the data is stored, it will be same unless you physically go and damage it. It is said that direct access, meaning that you could directly access which folder, which path, which stuff you need. Third is storage, optical disk or magnetic tape. These are storage that will be spinning. If you see, we call it a sequence access, meaning that if you see a CD, the CD will be spinning and spinning and spinning. It would be reading data in a sequence way, that's why it's spinning. And virtual memory means extend RAM using space. For example, if you take your phone, then they say that you can extend your RAM from 5 gig to 8 gig, or 4 gig to 8 gig, or from 8 gig to 12 gig. That additional 4 gigs are taken from your secondary memory. So that's how it works. So main memory, secondary memory, these are the type and these are the hierarchy. So this is the most important one. As I said, this is the architecture of 8085 without WZ. So we have register pairs, we have B, C, D, E, H, L, and this could be paired. We only pair B, C, D, E, H, L. We don't go and pair P, D, C, E. We just take the one that's beside them, B, C, D, H, L. And this H, L, we call it as memory. Sometimes we say it as memory, we call it as memory. So H, L is specifically used for memory. And stack pointer, where we save the memory location. For example, load SP and 299H, meaning that 299H, meaning that in stack pointer we mention that specific memory address, and the memory address will be taken, will be explained in a while. Program counter, it means that the next stuff that we need. Maybe now I'm executing 3000H in the origin, maybe it's move A, and in 3002 it may be at B. So program counter shows you the next instruction. When this instruction is running, it shows the next. So program counter actually shows the next instruction that should be running. Then in the same 8085 we have our ALU, we have our flag, we have our temporary register, accumulator. Accumulator is the main stuff here, so every data that's going in will be stored in the accumulator, then only we will be moving to B or C or D or E or so on, or sometimes we'll be direct accessing these memories, okay, these registers, sorry. Then our address are A to 15, meaning that, okay, let me explain it here. So we have this as our memory system, 2 power of 10 is KB and so on. So now we in 8085 we have 16 lines, so 16 lines means 2 power of 16, which is equivalent to this, or we call it 64 KB memory. So we have 16 bus lines, so 16 bus lines, which technically gives us to 2 power of 16, which gives us this value, which is equivalent to 64 KB. So the addressable location is equivalent to 2 of the address line, which is 16 line. Meanwhile, the 16 line is made as 8 and 8. We call it as PC low and PC high. If sometimes we are going to load, as I said, we have this BCDEHL memory where we could input 16-bit data, or we call it 2-byte data. So the 16-bit data are pushed as PC low, as the lower byte and higher byte. Meanwhile, we specifically allow this 7 bits to IO, which is for input output address. Maybe we are going to transfer data from our keyboard, our mouse, our sensor, so we specifically exclusively exclude it for the data transfer. Then we also have this control circuit for the 8085. Then we have the interrupt control. Interrupt control will be explained in the interrupt. Serial IO control, the S and IO will be explained in the IO series. Okay, so this is the basic of architecture of 8085. Then we also have, so this is our microprocessor. We have register, we have instruction decoder, we have ALU, we have control, and just similar to ALU, just it's quite different because it has the timing stuffs. Then we have control bus, data bus, address bus. So address bus is for memory, data bus is for IO, and control bus is to control, meaning it controls the read, write, move, add and everything. So 8-bit is equivalent to 1 byte, as I said here, and these are all connected to memory input and output, because input and output needs memory location, it needs data to transfer, and it also need control to be controlled. Okay, then we have a read or write operation, and so the operations are divided into control from CPU and send to CPU. So the control from CPU is read, write, clock, and interrupt, acknowledge, so we call it int A. And the one that sent to CPU is interrupt, request, and ready. So meaning that if a device is connected, the peripheral is connected, the peripheral will tell that device is ready, or it would send that the interrupt request. So interrupt acknowledge means, okay, I acknowledge your request, so it gives back, it's from CPU tells them, okay, you can read, you can write, the clock is on. This is something that's given to the CPU. Okay, so we have 4 types of stuff going on in the microprocessor. One is sequential operation, which is memory read write and IO read write. This is in sequence because you need to go through the memory, you need to go one by one. And for example, if we write the program in assembly language, we start from org800h and move A80h, then add A with B. The code is written in sequence from 1 to the final line that you have wrote, so that's sequential operation. Then we have internal operation. Internal operation means, for example, if my code says move A 20h, we need to fetch this code, we need to translate with this code, we need to execute this code, we need to store this, we need to pull this. So fetch, execute, store, retrieve, stack, these are all internal operations that being processed. The opcode means, for example, in the assembly language as well, we have move A20h, maybe we have a load stack pointer, maybe we have a load accumulator. So the first word, which is the command given, is the opcode, operational code, which is the first word. Maybe if I say MVI, move immediate, MOV, move, add, sub. So everything is declared by the first word that's in the line, which is the operational code. So that's what the opcode means. And internal architecture means this is the internal architecture. So this is the architecture of 8085. Internal architecture specifically means that this and this. Okay, so one, we also need to understand this. For example, this is the code given. So org 2000, we need to start at 2000's memory location. So we know that the memory locations is given from 0000 from FFFF. So it means that it starts from 2000. So as said that we have data area, program area and stack area. So in this case we mentioned that our stack area is around 2000. So this is 2000, this is 2 byte data, then this is also 2 byte, and this is 1 byte, and this is also 1 byte. So how do I know 2 byte, 2 byte, 1 byte, 1 byte? Need to refer to the 8085 instruction set. In some cases the instruction set is given in the appendix, or in some cases they will be given to the engineer. In this case we are just gonna see the overview, so I don't think we will be needing the instruction set. So I said that we are going to start in the 2000, so 2000, and move A 50H, meaning that the move A translate to this hex code, then this 50H translate to this hex code, meaning that it's 2 bytes. So we know that 2000 plus with 2, our next will be 2002. So 2002 reflects that move B. So here is 2002. So here is 2000. Another 2 byte, meaning that we will be going to 2004. I said that 2004 has add B. So 1 byte means it's 2005. So each line has the specific stuff. I said that the opcode lives in the stack. So this is 2 bytes. So the first byte is move A. So this is its hex code. Second byte. So in some cases it would be longer, maybe move A, maybe it's it's a 16-bit data, so you need to be familiarized with that. Then we have a bit movement, arithmetic movement, jump movement and instruction. These are something that will be explained in the later slides. So I said that n plus 1, n plus 2, it requires the byte 1, byte 2, byte 3 as what's explained in here. So these sometimes can be asked to the engineers. Okay, so be prepared. Then okay, this is the pair. Now the stack, actually stack means it's the memory, just it means that the instruction that's being pointed in the stack. Okay, so it works in the last in first out. So meaning that if I have FIFA and I put this in the stack, so meaning I put F first, I put I then, I put F then, I put A then, so it would become as such. So last in will come first, so it will come as AFIF. So technically it will be in this format, so you need to be familiarized with that. Now this is say that push HL. So we need to know that the stack pointer is, maybe the code was as such, load stack pointer 2099, then they would be telling that push HL, meaning that in 2099 we need to be there. Maybe the stack pointer, okay, it's not 2099, the stack pointer was lastly set to 2099. Okay, so in this case the stack pointer was lastly used and the last data was in 2099. Now in this case they say that push HL. Push HL means we have 42F2. This is our bit 42F2H. So this is divided into two. We have PC high here and PC low here. So we will load our PC high first, then PC low, because what I said is last in first out. We need our PC low as first out. Okay, so we load 42 in 2098 and F2 in 2097. Now it will rise, so our stack pointer will show 2097 as said. Now this is for pop. Okay, now what is pop? Okay, push pop it doesn't mean that this. Okay, push means send data to this stack pointer, meaning that if we write push HL, it will take the HL data and put. If I say push BC, it will take the BC data input. If I say push BC, it could be D600 here. Now pop BC means, it doesn't mean that pop BC, it means that pop the stack pointer data into BC. Okay, if push HL, push HL data into memory. Pop BC means pop memory into BC. Now our stack pointer shows that 2097, so 2097 should be popped out to low and 2098 to high, and the stack pointer should show 2099. So stack pointer shows 2099 and the F2 is in C and 42 is in B. Okay, what BC, this is for PC low, lower byte, PC high. So last in first out, last in first out mean last in was 42, it first out to lower, and the second one should be into higher. So this is how memory system works. We will be doing this in the assembly language sooner. Okay, then we have flags. So these are the flags. So we have sign flag, zero flag, then we have don't care, auxiliary carry flag, parity flag, and a carry flag. Auxiliary carry flag means that in our bits or bytes, maybe we have 8-bit data. In the 8-bit data, we split it as such. We have 4 lower, 4 higher. So if from this to here we have carry, maybe we have 0 0 0 0 1 0 0 0 in register A. In register B we have as such. So these two gives this, so there is a carry, then means our auxiliary flag will be 1. Okay, and then we have our carry means we have a carry here, this bit has a carry, so this is 1. And 0 means if all the data is 0, this means 1. If sign means if we take a large number, maybe 135 minus by 118b, we will be getting negative, so the sign will cause 1. And parity means the parity check. If the number of ones are odd or even, this will be 1, mostly if it's even. Okay, so this is for the flags. Then we have control logic subsystem, which is explained here, timing and control unit. So these are all stuff that's manually connected. So the ready, reset, in, hold are a manual button. Then crystal means crystal oscillator, which actually gives the clock. If we rely on our normal power, which we on and off, it doesn't actually gives the clock, so our clock will off here, then somewhere around we will be needing to restart. But if we have a crystal clock, the crystal clock will be up down at the moment. Now if in the normal clock out here we cut it here, then we suddenly on it, it will refer to the crystal clock and make it back to normal synchronization, to synchronize. So this is read and this is write, they are low active. This is enable latch, which is for the, we know that the address are from AO to A15, then we exclusively put AO to A7 for data, so these are required in ALE as okay. And then we need selection and IO or memory, which is for the AD, which is for the address line 0 to 15, where we exclusively put for 0 to 7 for the data. Then this is for the reset, clock out, and hold acknowledge. These are the one that is being controlled to the microprocessor and to the control unit. Okay, and then we have instruction cycle. Instruction cycle means this is one instruction cycle. Maybe if your program has move B, STA16H, move C, so this program has 3 instruction cycle. Okay, an instruction cycle has 4 machine cycle, meaning that it has fetch, read, this is lower, this is high, and write. Okay, so store means it opcode fetch, it's okay, take this. So store address, store STA means store in accumulator, so sorry, store accumulator into something. So store address maybe A280H. Okay, so it takes, oh, we need to do store. Okay, then it says the lower byte. Okay, then it says the higher byte, then it writes the bytes 2 and 3 content of register A. Okay, now this is for fetch. So opcode fetch actually has T4 till T6. It depends on the opcode. In this case, STA has 4 clock cycle. Okay, machine cycle means how many cycle that this specific instruction has, and T state means how many clock, meaning that how many specific clock pulse each machine cycle takes. In this case, a instruction cycle called STAADR has 4 machine cycle, which is fetch, read low, read high, and write. And that specified machine cycles has these T states, meaning that each clock pulse. Okay. Now, this is a diagram for the decrement B. Okay, so we will see opcode fetch machine cycle. As I said just now, this opcode for store has 4 T state, but here we have 6 T state for decrement X, but this is actually limited to 4. We extend it to 6, and now we will see this specific diagram. So our clock as this, it's not perfectly up and down because every rise is in a slope, it's not perfectly rising. Okay, now this is our clock. The status means that the additional external stuff that we are controlling, as one, the selection and also the memory read write. So 0 means the memory is on, the input output is off. Now A8 to A15 is for the higher program counter, sorry, higher it's called program counter, but we call it PC high, meaning that the lower byte and higher byte. Okay, so it's for the high. Now AD0 and AD7 is ALE, meaning that active latch enable was high, but it's using for lower byte, then here we use for higher byte. When the read is off, meaning that it's actively negatively active, meaning that it's active low. Yeah, active low means if it's 0, it's 1, it's working in a NOT gate. Okay, so when it's actively low, it changes into the data bus D0 to D7, but specifically we are playing with our memory, we don't actually bother this. Now in the specific T cycle, in T1 it's actually loading the PC low and PC high. The next 2 T cycle is actually loading the DO D7 due to the read is being low. Then we know that it's being unspecified. Specifically in this 6 T cycle, we could make this ready go up or ready go low. This 6 T cycle is specifically exclusively given to the decrement X DCX command. So more or less the DCX command will have T6 state, and this memory read, meaning that for example DXB decrement B, meaning that if our B had 06H, it would become, maybe we'll call it 06H. Decrement XB will become B into 05H. In order to do that, it should operate, it should fetch the code, it should read the code, and it should write the code where it's -1. Okay, so this is the basic in architecture of microprocessor system and what's happening and the basics. This would be needed for you to understand the upcoming lectures. Okay, thank you.